Well, hello. This video is going to help with 11.2, which is second derivative and graph. So what is the second derivative? It is the derivative of the derivative. So we know the derivative can be set equal to 0 and find critical values. We know that we could then use those critical values on a sign chart and find where it's increasing and decreasing the original function based on that derivative. Now, the second derivative will tell us whether something is concave up or concave down. So we have our definitions here. Let's add concave up, kind of looks like this, concave up, and concave down kind of looks like this. Now, it could be just a piece of that. Concave down could also look like this, or concave up could kind of look like this. So it doesn't have to be like the full U parabola shape, but concave up, concave down is kind of what we're looking at. So right now we can look at that derivative and we can see where something's increasing and decreasing critical values. And then now we're going to add this concave. So we can pretty much graph something from without a graphing calculator from all the information that we've learned. So we can look at the original and we can tell a bunch of different stuff about the original, like domain, range, all sorts of like asymptotes. We can look at the slope of a line. So we've learned a lot of tricks of how to graph from a regular original function. Now we can also use the derivative and second derivative tips to help us as well. So we can fully graph something without a graphing calculator. Now, no fun, but on the next exam, you will graph something with just given information, no calculator, using all of your information, right? Okay, so we have to look at some second derivatives, which isn't bad. And then the theorem, we have this thing called an inflection point here. It's found the same way you do a critical value. You set the second derivative equal to 0. So we still have the first derivative, but now if we set the second derivative equal to 0, that's an inflection point. And what that does is it tells you that point where you're going from concave up and maybe then switching and going to concave down, okay? So let me add a little page here real quick and go to that. So if I drew something, even like this, kind of like the last shape I drew, right? Here's our X, here's our Y. If I have something like this, right? We know it's increasing from here to here, but it's concave up all the way to about halfway to here. And then it starts to be concave down. Do you see that? So the inflection point is somewhere in here. It's not at the top. That's where we switch from increasing to decreasing. It's over here somewhere that's showing, okay, now we're going to go up and we're switching to start to concave the other way. So this is concave down, okay, concave up. So here's this graphing strategy that they give you here. And that graphing strategy it's basically the whole next section, or section 11.4, excuse me. It's like, okay, I'm going to look at the original function, step 1, and I can find all the domain, the intercepts. I can also find asymptotes. And then step 2 would be to analyze the first derivative. Step 3 would then be to look at this second derivative, and then you can sketch the function. That's where we're going. Okay, let's look at some concave stuff. So we have to know how to do the first and the second derivative. So look at this function here. What we start with is finding the first derivative. So the first derivative is 4 times 7 is 28. X to the third minus 2 times 11 is 22x minus 15. right? Then the 3 disappears. If I went to get the second derivative, we label it with 2 prime marks, right? Second derivative. Sometimes you see it with, well, do they get, I won't worry about it. You'll see it. It's the dy dx with the squares on them means second derivative as well. So if we look at this one, what is 3 times 28? 84. So 3 times 28 is 84, x squared minus 22. Now the x and the 15 drop off. So if it's a polynomial like this, it actually gets easier, right? Let's just do second derivative. Second derivative on 2 is pretty basic as well. We really just find our first derivative here. So 5 times 4 is 20, x to the 4th, plus, I don't know what 18/5 times 12 is. So 12 times 18/5 is 43.2, or you could do it as 2/16/5. Either way. And then it's x to the 18 divided by 5 minus 1 is 2.6, or 13/5. And that's our exponent, 13/5, or you could use 2.6. That's absolutely fine. Then the 19 drops off. So we go to do that second derivative, and 4 times 20 is 80x to the 3rd. Oops, somehow I missed my 0. 80x to the 3rd. And then we have 216/5, and then we're going to times that by 13/5. So I get 2,808 over 25. So 216 times 13 over 5 times 5, right? And then x to the 13 divided by 5 minus 1, and it's 1.6, or 8/5. All right, there we go. Remember, the fraction key is on the math side over here, first thing. So you can switch any decimal to a fraction. All right, so let's move on. So second derivative we'll still do in every single problem, so we'll get to some harder ones. Problem 3. I want to find the x and the y coordinate of some inflection points here. So first of all, I know I have to find the second derivative. So start with the first derivative. So I get 3 times 2 is 6x squared minus 18 times 2 is 36x plus 7. So there's our first derivative. Second derivative will then be 12x minus 36. So I went from an x to the 3rd to an x. So this is a line, which is fine. Now, if I want to find an inflection point, that is where the second derivative equals 0. So inflection point. Okay, is where 12x minus 36 equals 0. And this will only find the x value, and then we can find the y. So I'm going to add the 36 over, divide by 12, and I get x equals 3. So we know x equals 3. So everything we're finding using the first derivative, using the second derivative, they're all information about the original. So if I want to find y, I have to put it into the original. Okay, so I have to then take f original of 3, and that then gives me, 2 times 3 squared, to the 3rd, minus 18 times 3 squared plus 7 times 3 minus 11. Oops, I couldn't quite fit the 11 on there. Okay, so if I figure that out, I get negative 98. So the inflection point is at 3, negative 98. So that's the point where we're switching from concave up to concave down. Okay, so then the next one, and it doesn't ask us for where it is concave up or down, but the next one does. How are we going to do that? Well, we're going to do it just like we do increasing, decreasing, but this time we'll do everything with the second derivative. Where does the second derivative equal 0? Where are those inflection x values? Put them on a sign chart. Where is the second derivative positive? Where is the second derivative negative? So start with that derivative. So 8x to the third minus 96 x. And then we go from here to second derivative, 24x squared minus 96. Okay, then we have to find where does that equal 0? This is for our inflection points, because it's of the second derivative. So 24x squared minus 96, where does that equal 0? Add your 96 over, divide, I get x squared equals 4. So x is equal to positive or negative 2, square root of 4. So those are our two inflection points. We don't have any partition numbers because we still don't have an x in the denominator. So we're still going to do our sign chart of -2 and 2, but this sign chart will be of the second derivative instead of the first. These are still zeros, not ND, not defined, because they are from getting where the second derivative equals 0. Okay, then from here, we're going to do a little chart with that second derivative, right? And that is 24x squared minus 96. So we're going to put in a value less than -2, so maybe -3. And I don't know, -3. Did I have it written down? Dang, I'm going to have to find them all. Just kidding. 1, 2, 3. Oh, maybe I don't know. Where's that from? I was going to cheat and not have to put them in, but by the time I find them all, I could have put the numbers in. It's fine. 24 times -3 squared minus 96. I get a positive 120. Okay. And something between -2 and 2 is maybe 0. So 0 minus 96 is negative. And then last one would be above, which is maybe 3. So 24 times 3 squared minus 96. So 24 times 9 minus 96 is again a positive. So I went positive, negative, 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 positive. So the way that I list this is I'm concave up from -infinity to -2 and from 2 to infinity, and I'm concave down from -2 to 2, okay? And my inflection points are here at x equals -2 and 2. I don't really care about the y unless it asks me. Okay, so let's look at what this one looks like. Gosh, so let's put this in Desmos. I was like, where's my problem? Gosh, this is a lot. Here it is, I betcha. I wanted it because I want to be able to type it in without having to look back. So the original function goes 2x to the fourth minus 48, x to the second power equals y. You don't always have to have the y part, but and then we can kind of scroll I can't scroll that out very good. It doesn't really want to. There we go. Little. Come on. I was using 2 fingers. Whatever. Way down here are my increasing, decreasing spots, right? That's increasing, decreasing. And we didn't do the first derivative on this one, so we don't really care too much. But we can see that's concave up all the way to this spot that I'm blinking. So it's concave up for that. And then it's concave down for the middle and then back. And remember, it changes concave in the middle here somewhere. What value did we say that was at? At 2 and -2. So it should be at 2 and -2. Let's see here. So if we do x equals -2, we can kind of see that just to kind of see where it crosses a little bit easier. So it's right in here. It is. So at -2, -160 is one of our inflection points because that's where it's going down. And then, man, it's starting to go up and then curve down, right? So, all right. Oops, not OneDrive. So let's look at another one. That one's pretty much the same. I kind of want it to be harder. Go, let's look at 6. So if we look at problem 6, it's saying, it's on there. We have 16e to the x minus 2e to the 2x. So for this one, what we want is we want to find the second derivative and then find those critical values and tell me where it's concave up and concave down, okay, and inflection points. So let's start with that first derivative. And the first derivative of 16e to the x is 16e to the x. We don't have anything with the x, so there's no chain rule. Then we have minus, what's this going to be here is we have a chain rule here because you have a 2 with the x, so what's the derivative of 2x? 2. So the derivative of this exponent is 2. So we have to times by a 2. So what we'll do is we'll still have 2e to the 2x, right? But then I have to times it by the extra 2. So I'm going to simplify this. So we'd write it as 16e to the x minus 4e to the 2x. Derivative again. Okay, so 16e to the x, wow, stays 16e to the x. But what's going to happen over here is we're going to times by another 2 because the derivative of the exponent there is 2. So when we simplify this, it's 16e to the x minus 8e to the 2x. So that 8 will be missed by a lot of people because 2x where we don't notice, like, it's not just x. We have to do the derivative of that and times it outside. Okay, so this is our second derivative. So for inflection points, right, we're going to say we're 0 equals the 16e to the x minus 8e to the 2x. So we can look at this and we can actually take out an e to the x because e to the x can't be 0. Okay, so let's take out an e to the x. And that's going to leave 16 minus, this will still be an 8. I guess I could have taken out the 8 too. And over here, this will be e to the x. Because if I say I have 2 x's, okay, then from here, I'm second guessing myself on that part, but I'm pretty sure I'm right. Do you like that? Pretty sure. This doesn't show me, but we'd have the 16e to the x. Yeah. Take out. They don't really show the factor part. Second derivative. Well, they do it that way. 2 to the x. Can't equal 0. And then they did it totally weird. Okay, so Let me see how I did it in my e to the x. Yeah. So I take it out. That one's a little bit different. I'm always going to have to take out the e to the x part usually because it can't equal 0. All right, so I'm going to keep going. So this first factor, e to the x, can't equal 0. So there's no solution on this part. But we can look at 0 equals 16 minus 8 e to the x. So I could add the 16 over, or minus the 16 over. And then divide by the negative 8, divide by the negative 8. And that's going to give me positive 2 equals e to the x. Then I can go ahead and use logs to solve this one. So the log of both sides would be log of 2 equals log of e to the x. Okay, so that brings the x out front, log of e. What does log of e mean again? Or give you? 1. So this really is just natural log of 2 for x. And we don't want to estimate it. We want to leave it natural log of 2, but we might want the estimation for our sign chart just so we know about where it's at. So our sign chart is just going to have the natural log of 2. We're going to do this with the second derivative. And I'll draw a little line there for my sign chart. And this is about 0.69 positive. So then we have a clue where that's at. Okay, so from here, what number is less than 0.69 would be, I don't know, 0, right? So we can take and do a little chart here. Okay, and our second derivative was 16 e to the x minus 8 e to the negative 2x. Okay, so then we're going to put in 0. And what are we going to get out? Well, 16 e to the 0 minus 8 e to the 0, because 2 times 0. That's going to give me 16 minus 8. So that's going to give me a positive answer. So positive, positive, positive. And then on the other side, I don't know, maybe use 1. So 16 e to the 1 minus 8 e to the 1. I have to use the calculator for that one. E to the 0 is 1, so that other one was easier. So 16, and then e is above the log to the 1 is like 2.6 something minus 8 times another e to the 1. I get about 21-ish. So I got positive. E, did I do minus on my calculator? 17, 16 e to the 2x. Oh, shoot, this would be 2. I just put it in as 1 for some reason. I was like, I did something wrong. This is negative. And I like the rest is correct. So when I put it in at 16, e, okay, so 16 e to the first for this one here, right? And then minus 8 e to the 2 times 1 is 2. And then that gives me a negative. Phew. I was like, I don't have the right answer. So our sign chart says positive to negative. So where are we concave up? Where it's positive. So we're concave up from negative infinity to the natural log of 2. We don't want to use the 0.69. And then we're concave down from the natural log of 2 to infinity. Okay, and then our inflection point, x equals natural log of 2. If I had to find the y, this one, the y is 24. So if you had to find the y, you go all the way back to this original and you put in for those x's the natural log of 2. It works out pretty because if you put it in your calculator, if you go e to the power of natural log of 2 It is actually just 2 because you're like e to a natural log of 2 is 2. So it ends up being 16 times 2 minus 2 times, well, you got a 2x in there. So it ends up being 24. Okay. So that's what we're looking for. This one's definitely a little harder with the logs. And you have to be able to factor out a log, an E, or both, right? So we have to be able to factor out an E to be able to find those inflection points on almost every E problem. Okay, so what I'm going to do is that's the end of this packet. If I find any other problems that I found are kind of challenging, I will just make a part 2 for you. Okay, catch you later.